We're asked to find the first and second derivatives of this function. So it looks like it's a good one for the quotient rule. The derivative is found by taking a derivative of the numerator function times the denominator function kept the same, subtracted by the numerator function times the derivative of the denominator function. So the derivative of 7 plus x squared is 2x, all over the denominator function being squared. So there's our derivative. We can clean it up a bit, combine like terms up here. This is minus a 2x squared. So x squared minus 2x squared, this is 7 minus x squared in the numerator. Then it's 7 plus x squared being squared in the denominator. There's our first derivative. The second derivative is found the same way using the quotient rule. It's the derivative of the numerator function times the denominator function. Denominator function is just a lot bigger this time. 7 plus x squared being squared. Then we subtract that by the numerator function times the derivative of the denominator function. Now the derivative requires the chain rule, right? The derivative, do this off to the side, the derivative of 7 plus x squared squared is 2 times 7 plus x squared, because the power comes down, multiplies, then it's reduced by 1, so now it's the first power. That's a derivative of an outermost function. The derivative inside the parentheses is 2x. So the derivative could be listed as 4x times 7 plus x squared. That's what needs to multiply up here. It's the derivative of the denominator function. So it's 4x times 7 plus x squared. That's all over the denominator function squared. So this is now 7 plus x squared to the 4th power, because you raised this to the 2nd power, and powers on top of powers multiply. So we can clean it up a little bit algebraically. Oh, it'll take a while though. I'll expand this because we want to eventually collect some like terms. So that's 49 plus 7x squared plus 7x squared. So that's going to be 14x squared plus x to the 4th. And then over here it's minus. I'm going to distribute that 4x first. Four x to the 3rd. That's all over 7 plus x squared to the 4th. Okay, so I can keep expanding. I can multiply this to everything, the negative 2x. So it's negative 98x subtracted by 28x to the 3rd, subtracted by 2x to the 5th, and then you subtract that by the result. So I'm going to keep the result in parentheses. So 196x, and 7 times 4 is 28x to the 3rd, then subtract 28x to the 3rd. Let's cancel out nicely. The negative x squared times 4x to the 3rd, that's negative 4x to the 5th, all over 7 plus x squared to the 4th. Like with a lot of the problems in this textbook, the calculus has been over for a while. Now it's just a bunch of algebra. Okay, combining like terms. Let's see, the highest power is x to the 5th. So negative 2x to the 5th subtracted by a negative 4x to the 5th. It's negative 2x to the 5th plus 4x to the 5th. So it's 2x to the 5th. So I took care of those. And no x to the 4ths. X to the 3rds, these cancel out. We're left with just a minus 28x to the third. And then negative 98x subtracted by 196, so negative 294x. And then if we factor out a 2x from the numerator, you've got x to the fourth minus 14x squared minus 147. Let me double check that. That's all over 7 plus x squared to the fourth. We can actually factor this parentheses. You can find two numbers that multiply to be, let's see, can we? Two numbers that multiply to be 147, but add it to be negative 14. Okay, so that's it. So we can factor the numerator. It's going to be x squared in each of the parentheses. That way x squared times x squared makes x to the fourth. And then what we want is minus 21 plus 7, because I think negative 21 times 7, yeah, that makes negative 147. And negative 21 plus 7 makes negative 14. Okay, so what we have is that there's 4 7 plus x squareds in the denominator. There's 1 in the numerator, so we can cancel 1 in the numerator and 1 in the denominator. So this is the second derivative. Okay, so to answer the rest of the questions on this problem, we're supposed to find where it's concave up or concave down, so we need the second derivative. It's concave up where the second derivative is positive. So you want to set the second derivative equal to 0 and solve, because then you're going to find all the places where it could potentially switch from positive to negative or vice versa. So the first step in solving this equation would be to multiply both sides by 7 plus x squared to the third power. So it makes this cancel out, and you're left with 0 equals 2x x squared minus 21. And so if you solve that, you're going to have x equals 0, x equals square root of 21, positive or negative. Those are the three places where the second derivative could switch from positive to negative. 0, square root of 21, and then negative square root of 21. And so like always, you just want to test some points around those to find out whether it's positive or negative. Remember, this is the second derivative, so we're finding concavity. So what is the square root of 21? I don't even know. 4.5. So let's just test x equals negative 5. That's something to the left. Let's test x equals 1. Negative 1, I should say. Let's test x equals positive 1. And let's test x equals 5. Now give us the signs between all these potential inflection points. And so again, you're plugging these into the second derivative. So we're plugging them into what we just found for the second derivative here. We don't need to know the number. We just need to know whether it's going to be positive or negative. And look, in the second derivative, the bottom is always positive, because no matter what you plug in for x, it's going to get squared. It's going to be turned to a positive number, then added to 7. So the bottom is always positive, so the top part's the key. If I plug in negative 5 into the top, negative 5 squared is 25. 25 minus 1 is 4. 4 times a negative is going to give us a negative. We have a negative divided by a positive, so this is going to be negative over here. And then let's do the same thing if we plug in negative 1. Again, the denominator is always positive in our second derivative. So negative 1 squared is 1. 1 minus 21 gives us negative 20. Negative 20 times negative, this switches to a positive number. Again, we don't care what the number is. We just want to know whether it's positive or negative. X equals 0 is another potential inflection point. So between we've got everything between these two, negative square root of 21 and 0. Now we need to check between 0 and 21, and that's where we can plug in a test point. If you plug in 1 minus 21 gives us negative 20. Negative 20 times 1 is negative. Negative divided by positive is negative, so 0 is also an inflection point. And then if you plug in 5, you get a positive number on the top and a positive number on the bottom, so it's going to be positive. So we just found out that these are all inflection points. It's concave up, on the intervals negative square root of 21, 0, because that's where it's positive. Then we put a union, and then it's square root of 21 to infinity. That's where it's concave up. And then it's concave down from negative infinity to negative square root of 21, because that's where the second derivative is negative. And then it's concave down between 0, so we need a union. Oh, I'm missing a parenthesis here. There we go. Now it's concave down also between 0 and square root of 21, because that's negative between those two. And then they want you to determine all local extrema using the second derivative test. So local extrema are like local maxes, local mins. Okay, and that's where we identify potential local maxes, local mins by finding critical points. We set the derivative equal to 0 and then solve. And the second derivative test, it says that it's a local max if the second derivative is negative, because that means it's reached a point and it's slowing down. I can show you why. Okay, so here's our x and y grid. Here is a random function. So the first derivative is 0 when you hit a local max, right? Because it's completely leveled off. Now the second derivative is negative here. It's a local max if the second derivative is negative, because the second derivative is measuring how fast the slopes are changing. You got a positive slope. You got a smaller positive slope. Smaller, 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 smaller. Your slopes are decreasing, so the second derivative is negative. So local max are where the first derivative equals 0 and where the second derivative is some sort of negative number. And local min are where the first derivative equals 0 and when the second derivative equals a positive number. So here's our first derivative. If you set that equal to 0 and solve, you should get critical points at x equals positive or negative square root of 7. And then if you plug in positive 7 into your second derivative, which was this right here, if you plug in positive square root of 7 in here, square root of 7 square root of 7, 7 minus 21 is a negative something, and negative times positive is going to give you negative. You got a negative in the numerator and a positive number in the denominator. So that means square root of 7 is a max. Because the second derivative was negative, I didn't even bother figuring out exactly what it is. I just know the sign's going to be negative. And because the first derivative was 0 at x equals square root of 7. Do the same thing for negative square root of 7. You'll find out it's a local min. Because if you plug in negative square root of 7, you should get a positive over a positive. The second derivative is positive, and the first derivative is 0. So that would be your local min.